Hey guys, we are continuing our week of being off because of the snow and ice. Not sure when we will be back in school this week or if we will probably just see each other next Monday, which is my bet personally. However, we're going to continue on with Newton's laws. So, first of all, I really hope that you guys all have internet access and heat and electricity, top priorities there, and then followed by internet access sometimes. I hope you're staying warm and inside where it's very, very nice. And staying out of that awful, dreadful wind chill of in the negative 20s is like a record for my lifetime. So you've lived through that now, in addition to the global pandemic. So check mark that off the list. And that you are drinking as much hot chocolate as you could possibly ever ask for. All right. So today I am just going to briefly explain Newton's second law, and then we're going to move on to explaining the assignment. So it's going to be short, quick and to the point. First thing, after checking your guys' assignments from Monday about Newton's just second law problems, there was one question that asked about inertia. I just want to clarify something. So inertia only refers to how difficult it is to first move something. And it's not affected at all by how fast that thing is moving. It's just affected by like how big it is, how much mass. So there was a question about an apple versus a grapefruit, where the grapefruit's obviously bigger than the apple, but the grapefruit's also moving faster. Well, the grapefruit still has more inertia. You still have to push the grapefruit harder to get it to move in the first place, and that's what determines its inertia whenever we're talking about Newton's first law. So just know this is like the most commonly missed one that I noticed, and so I just wanted to go over that with you guys. Everything else I tried to respond to, so just make sure that you have double check them in preparation for things. All right, so Newton's second law is pretty simple, honestly. It's really just the equation, but it has a farther reaching idea behind it than you would at first think. So Newton's second law states that the force that is placed on an object is equal to the mass multiplied by the acceleration. So this means a couple different things. So it means, number one, that the more mass an object has, the more force is required in order to accelerate it. So it tells us that with the same force applied, you can accelerate a small mass much farther. So if I think about if I have two things on wheels and one of them is a much heavier object and one of them is lighter, and if I just give them both the same push, then the one that is lighter is going to be able to accelerate at a faster rate. So don't forget, whenever we talk about acceleration, we're not just talking about moving. It's not just how difficult it is to get an object to move. It's how difficult is it to get an object to change its motion, to either speed up or slow down or change directions. So this means that mass and acceleration are inversely proportional, which just means as one goes down, the other one goes up. So as things get heavier, it's harder to make them accelerate. And as things get lighter, it's easier to make them accelerate. So it's easier to move things that are light. It's harder to move things that are heavy. All right, so both of these things, we've got a school bus here. It took me a while to find one that has a Bentonville, by the way. So, hey, maybe that's someone's house. And this skateboard here, I think I already explained this in a different video, but if you gave them both the same force, so if maybe we had like a launcher, I don't know, just like a big old spring, and we tried to springboard both of these things, then it would be a lot easier to accelerate the skateboard to a much faster speed than the Bentonville school bus. That springboard launcher might not even work. Okay. This brings me to my next thing. There's an ADI lab posted on Google Classroom. Some of you have turned this in repeatedly. We haven't done it yet. It's in class. Don't worry about it. I know that there was a due date on it, but the due date, you haven't done the lab yet. I posted it last week, and I thought that we would for sure be back in school by now. But I was wrong. So we will do this whenever we eventually return. Don't worry about it yet. Oh, okay. So this is the thing we need. All right, Newton's second law can be explained using this equation: force equals mass times acceleration. Once again, we measure forces in newtons only. Mass is measured in kilograms. A quick reference point is that 1 kilogram equals about 2.2 pounds. So if you know how much something weighs in pounds, if you kind of just cut it in half, then that's about what it weighs in kilograms. That's not an exact, obviously, but I think it helps sometimes just to have like a reference point. So if you weigh, let's say 130 pounds, then it's about 75 kilograms, roughly. And then finally, acceleration is measured in meters per second squared. Now, let's take a look at this little 2. You guys obviously know that to square something means to multiply it by itself. However, this is part of the unit. The 2 means that the seconds are being squared. It's how we separate velocity from acceleration. Don't worry about it too much. You don't have to do anything with this, with the 2. You don't have to square the time. You don't have to square any part of acceleration. It just gets attached onto the end. That's it. And it's over with. All right, so using this formula triangle, so the F is on top, which means F is equal to m times multiplied by A. If I wanted to find mass, then mass would be equal to F divided by A. And if I wanted to find acceleration, then acceleration would be equal to F divided by m. So where the placement is helps you determine what you're supposed to do here. All right, last but not least for the notes section of today is friction. Friction is something we talk about often. Friction is usually the force that stops objects or slows them down, so it accelerates them in the opposite direction of the one that they are moving. Today we're going to look at an interactive in which there is no friction. So we're going to set friction to 0. And by doing so, we're going to make it to where the net force on an object is the exact same as the applied force that we put on the object. So don't worry about the different types of friction. Just know that for today, we're not going to have friction. And interestingly enough, if you wanted to do a good experiment, then having this snowy and sort of icy surface outside is a great example of the closest we can get to as little friction as possible without either creating a vacuum or launching us all into space. All right, so with that, today's assignment, here, let's start here. Okay, it's going to be called Week 24 Wednesday, Physics Classroom Interactive. I'm going to attach it though later. You need to turn it in by midnight in order to be counted present. So that's how we are taking attendance for today. There's no Google Meets. I'll put that somewhere in bold up at the top. You got 2 links. That's the one good thing about working from home is having 2 monitors. All right, here we go. Okay, so one link takes you to GoFormative. Hello, GoFormative. Of which this briefly explains all the things I'm about to explain. But I think sometimes hearing just instructions, it helps us a lot. The interactive, you're going to click here. However, it is also posted in Classroom as well. This is Physics Classroom. I love Physics Classroom. It's great. It has a bunch of different kind of sort of like online lab type things. And it also has a pretty good, not textbook, it's like short explanations of what these things are. So if you ever need a tutorial, if you ever just want to learn like more about the actual topic, you can click on Physics Tutorial and it walks you through like all the main things. So we're in Newton's laws. So there's a whole section here that just explains Newton's second law in perhaps a better way than I am. So you can click on it and it asks you like some check questions and it can check for you. And it's just overall just great. Okay, but that's not the thing we want. We want this guy. All right, so this is the interactive. People, for some reason, always forgot this last year. You click here to make it bigger. Don't strain your eyes and just keep it on that screen. All right, we click start first, and this is the screen you'll get. We're going to keep friction at 0. Do not touch those buttons. And then the applied force and the mass we can change. And we're going to change them according to what it says on the table in the GoFormative. So 10 is the limit for force, 1 is the limit for mass, and we can click up or down in order to change these things. So let's click 1 and 10, okay? We're just leave it on the thing. So now we're gonna push, and you'll notice that the net force is 10 newtons, which is the exact same as the applied force. Now, if we had friction, which was pushing the box in, say, the opposite direction, friction would go to the left, the applied force would go to the right. I just realized this camera is backwards. And either way, we would subtract those from each other, and that's how we would find the net force. But since there's no friction, there's no net force, or the net force is the same, so we don't worry about it. All right. Now, the point of this is for you to take this information and this velocity time graph. So remember, velocity over time, that's acceleration. That tells us the change. So the slope of this line is how we're going to calculate acceleration. So if you click on any of these little points, it tells you your coordinate. And if I remember, my acceleration is the same thing as slope. So slope is where we go up and then over. So here I go up 10 and over 1. I go up another 10 and over 1. I go up 10 and over another 1, and so on and so forth, because it's a straight line. So 10 divided by 1 is equal to 10, which means that my acceleration here is 10 meters per second squared. Okay? Bring this back to the interactive. So I actually did the first one for you already today, which is, oh, this is with 10 and 2. Okay. So over here, you're going to set the applied force. You're going to change it. It could be anywhere from 10 to 100. Then you're going to change the mass, either 1 to 5. You're going to write the net force. The net force is always going to be the same as the applied force. I crossed out the giant box that says velocity time information because you don't need it, because we would just be describing how that was constant. And then the acceleration, you are going to calculate, as it says over here before you ask, you're going to calculate that by finding the slope. So how much does it go up divided by how much does it go over? Okay. Then it asks you like 3 questions about these things. So if I double the force, what happens to the acceleration? So is it easier to make something move faster if you apply more force, or is it harder? If you want something to move really, really fast, is it better for it to be a higher mass or a lower mass? If I change both things at once, then why is that bad? Explain what we just did. Have you played in the snow? If so, what did you do? I attempted to sled down a hill. However, I left my sled at my parents' house the last time I was there. And so because of that, I had to use a plastic lid and it broke. So that was a little disappointing, and that kind of ended my time playing in the snow. But my dogs greatly enjoyed it. So that is my story for the day. I know you didn't ask. All right. If you guys have any questions, please email us, either me and Mr. Thomas or Miss Green if you have our class. And stay warm.